Okay. Today, what I'd like to do is I'm going to finish our discussion of the boundary correction for systems like the scalar wave and for general, and the same arguments apply to the generalized harmonic system. And after doing that, then I'm going to go ahead and we'll see how much time is left, but I want to say something after all this theory of how the method works about what the Spectre code using these discontinuous Galerkin methods has been able to do with binary black holes so far. So I'll switch over to the computer and have some slides to show you some results for the last little part of the last lecture this week. Okay, so to start out, let's come back to this issue of characteristic fields and speeds. So we've seen this, we saw this yesterday in 3D and today in 1D with Harold. So let me remind you, for the scalar wave system, so for the scalar wave, we have variables, U alpha, and when we reduce to first order form, those variables were the wave amplitude, which I keep calling G because of the analogy with the generalized harmonic system, where it would be the space-time metric taking this role, and then minus the time derivative of G and the spatial derivative of G. Okay. Now, that's how we describe the system in the volume. But what we're especially concerned with now, wrapping things up, is how do we handle the boundaries between the elements? So imagine this here is your element omega k, and it has some unit normal nk. And we're going to call this nk int, because we'll call the element we're thinking about the interior, and we'll call its neighbor element the exterior. It doesn't have to be to the right. Of course, there's going to be an element on each side of it, and they're not necessarily rectangles either. This is just for simplicity. And then here is nk exterior, and here is nk interior. Okay. So ultimately, what we want to understand is what kind of interior boundary condition do we put here? And just like Harold was saying in the earlier session, the way to understand that is to think about characteristic fields. The characteristic fields are the combinations of the evolution variables that propagate, at least in the high frequency limit, you can think of them as propagating independently as waves at some speed, either out of the boundary or in through the boundary into your domain. And so those are the things we care about, because anything coming into your domain is what you need to put a boundary condition on. And the characteristic variables are the combinations that are independently flowing across the boundary one way or the other. Or maybe they have zero speed, but that's what they are. So we need to figure out what the characteristic speeds are. Now, once you introduce a boundary with a normal direction, this is the direction you're imagining the waves are traveling, this n direction that Harold was talking about, then it's more useful to decompose these variables into a g pi, but instead of decomposing phi into phi x, y, and z, the component of phi in the normal direction is more, that's a terrible looking n, okay. In the normal direction, nl phi l is an especially important component that's treated differently than the others. The others, I'll just leave in here in this thing that I was calling phi parallel j yesterday. And this has the same information in it. There's two independent components in here. And if you dot the normal vector into this, because it's tangent to the surface, you would get 0. So this was just to remind you where we were at yesterday. Now, just like, I guess another thing we're going to want to keep around for a while is the form of the equations that we're thinking about here. So in vacuum, the set of equations can be reduced to a first order form where you have time derivatives of U alpha, no flux terms. We're assuming we're dealing with a system that isn't one of these matter systems where you have flux, it's not one of these flux conservative or flux balanced equations. So the only other derivative terms are these B, I, alpha beta partial I u beta. And then there's source terms. But yeah, so we'll just write the source terms, and that's equal to 0. But I'm not going to leave the source terms there long, because to understand the flow across the boundary, really only the terms with the derivatives matter for that. So I'm going to erase this right away and just change this to the principal part of these equations, meaning only the terms with the highest order derivatives, which here are just the first order derivatives, because we've reduced everything to first order. That's equal to 0. And what we found was if you take this set of three matrices and take its components, take its normal components, say N, L, B, L, alpha, beta, this now just has two indices. It's just a matrix. And I wrote it down yesterday. I'm not going to write all the components out again, but you can think of this thing as a matrix. So, you know. And once you have a matrix, you can find eigenvectors and eigenvalues of it. And as we heard in the previous session today and yesterday, when we were talking about it yesterday in the second session, the left eigenvalues, the left eigenvectors of this system determine the characteristic speeds, and the eigenvalue, sorry, the characteristic fields, and the eigenvalues are the characteristic speeds. So let me say that again. So the eigenvalues of this matrix here, and yesterday, maybe this was a little confusing. Usually you call eigenvalues lambda, and alpha hat can label them, but I'm going to call the eigenvalues instead V alpha hat, because it turns out those eigenvalues are the speeds that these combinations of the variables travel at across the boundary one way or the other. So yesterday when I did the eigenvalue problem, I didn't have minus lambdas down the diagonal, I had minus V's, because the eigenvalues turn out to be the velocities of these combinations of the variables. So these are the characteristic speeds. And then the characteristic fields, well, they're not exactly the eigenvectors. What they are is, Harold had a different notation than is in my notes, so he called the eigenvectors L. I'm just going to call the eigenvectors E alpha hat alpha. So the alpha hat labels which eigenvector you have, and the alpha is just the vector index from the alphas and betas in this matrix here. And this is the eigenvector. So this is the maybe this is getting too close to the screen. I'll just write it down here. Eigenvector E alpha alpha. But you have to take that and then and then sum over alpha, multiply that by the U alphas, the variables, and sum over them. That is what the characteristic fields are. And I'm going to call them W alpha hat. So when I use a lowercase w alpha hat, those are the combination of these variables that make the characteristic fields, whereas U alpha are the variables we're actually evolving. So that was just to set up some notation and remind you about some of the things that we were doing yesterday. For the scalar wave system, so far this is all generic, except for the scalar wave system, I've said what these U's are. Now what I'd like to do next is remind you what the characteristic fields happen to be when we took the eigenvectors of this B matrix that follows from the scalar wave equation. Yesterday we found that the eigenvectors, that the characteristic speeds, V alpha hat for the scalar wave system, well, it turns out there's 4 of them in 3 dimensions of space. The first 2 are 0, then there's one that's +1, and then there's one that's -1. We'll just call that a 1. So those are the characteristic speeds. Each one of those speeds is the speed of a high frequency wave mode traveling across this boundary. And negative means in the opposite direction as the normal, in to the element. Positive means out of the element. Then We also had the characteristic fields, which I'll call W alpha hat. And those turned out to be equal to G, that's one of them. Phi parallel J is another one. And then the last two were pi plus the normal component of phi. And then, so maybe I'll put commas in so it's clear that this is sort of like a vector. And then pi minus NL phi L. Okay, so this is where we left things yesterday. We found the eigenvalues, and then it turns out, I don't think I did all the algebra, but if you plug the eigenvalues back in and look for the eigenvectors, you get these corresponding eigenvectors. These two travel at 0 speed, but this one corresponds to a wave mode traveling out of the element, omega k, and this one amounts to something traveling in. We're going to hang on to these. Now, you can notice something about these combinations. These combinations, these are just linear combinations of the variables. And they're linear combinations of the variables because of this definition of the characteristic fields here. You can think of E alpha hat alpha as a matrix with two indices. Alpha hat is a characteristic field index. It says which one of these 4 characteristic fields you've got. And U alpha is the evolved variables. So if you want to, so you can actually think of this as a matrix of all the eigenvectors. And when you multiply that matrix by the characteristic fields, by the evolved variables, when you multiply that matrix by the evolved variables, then what comes out is the characteristic fields. So in fact, if you think of all the eigenvectors, E alpha hat alpha, and put them all together as a matrix, you can think of E alpha hat alpha as a matrix that transforms the characteristic speeds into, a matrix that transforms the evolved variables into the characteristic speed variables. Let me try to say that again. This is a transformation matrix. I'm going to call it T inverse, and I'll invert it to get T later, alpha hat alpha. And what this does is it transforms the evolved variables, U alpha, into the characteristic variables, W alpha hat. The inverse of this matrix T will transform the characteristic variables back into the evolved variables. And this matrix, it's called inverse. This is the one that's the inverse because somebody, at least in the convention we used, decided that the matrix without the inverse takes you from the characteristic fields back into the evolved variables. So to go from the evolved variables to the characteristics, then it would be the inverse of this. But you can just think of this as some linear transformation matrix. It takes a linear combination of your evolved variables. Now, if you look at what these are, you can figure out what that T has to be. So, because if you take this T and multiply it by your U alpha, so G pi, the normal component of phi, and then the tangential components of phi, the component along the normal of the element and the component tangent to the boundary, then when you do matrix multiplication, you'd better get back these 4 things. So like the first row is just going to be 1, 0, 0, 0, right? Because you just want G plus 0 plus 0 plus 0 to give you that. The second row is just going to be 0, 0, 0, and a 1, because the second one is also just a single variable. And then the third one, well, there's no G in it, so that's going to be 0 times G. There's no phi parallel, that's going to be 0, but now it's got plus, oh wait, there is a pi, sorry, so that's 1. So 0G plus pi plus the normal component, that's a plus 1, but no phi parallel, so that's 0. And then the last one doesn't have G, does have a plus pi, but it has a minus 1. So this transformation matrix is just a bunch of zeros and ones, and it looks like this. If you wanted to have the matrix T, which instead takes you from the characteristic fields back into the evolved variables, all you have to do is take the inverse of this 4x4 matrix. I'm not going to work that out, try to work that out on the board, but I worked it out. Myself at home, and I'll just tell you what the answer is. So T alpha hat. This is the inverse of this matrix. We're going to need it in a little bit. That turns out to be, let's see here. Well, this one is still 1, 0, 0, 0, and the next, and then this one is going to be, turns out to be 0, 0, 1 half, 1 half, and then 0, 0, 1 half minus 1 half, and then 0, 1, 0, 0. It so turns out that if you take this matrix and multiply it by this matrix, you get the identity matrix. We're going to use these in a minute. The next thing we're going to do is use these matrices to explain what boundary correction term we want to use here. Are there any questions about anything I've written here so far? Yeah.
These are matrices of numbers only because of this very special case.
Yeah, so that's a good question. The question is, why are these matrices, is it special that these are matrices only of numbers? And the answer to that is yeah. It has to do with the fact that this matrix is all zeros and ones, except there's one nj in there, and that's a normal vector. So that can also turn into a number if you multiply it by another normal vector. In general, these matrices, they don't depend on the evolved variables, but they can depend on space in principle. Yeah. Oh, sorry.
The B will never have. The Bi alpha beta will never have any of U alphas.
Oh, sorry. No, the B. Yeah, that's true. I should have said that. So the B is not allowed to depend on the derivatives. In principle, it is allowed to depend on the U's, but in the scalar wave case, it doesn't.
So when it does,
but in general, it does. Yeah.
You just evaluate it on the wall, on the boundary.
Yeah. So because I'm taking the normal component of it to the boundary, everything I'm doing with characteristic fields and speeds only is defined on the boundary. Without the boundary, you don't have a normal. So then breaking things up into these components doesn't make sense. And this whole argument of imagining traveling waves in one particular direction, well, there's no special direction when you don't have some surface to define a normal.
No, now what is going to happen is that NLB L alpha beta is going to have some components which depend on the fields themselves. So how do you calculate it and take its inverse? You need some numbers to take inverses, right?
Yeah, let me think about that for a second. So the question is, if B depends on the fields, which it's allowed to do in general, then how do you do all this? And I think, let me think for a second. I think you would still do the same thing. I don't know, Harold, do you have anything to add to that? The question is, if this B matrix happens to not just have numbers and space, but depends on the variables, the U alphas, then do you still do this same process, or do you have to modify it to get the characteristic fields? And I think it's the same, but I want to make sure I wasn't missing something.
What we have for scalar waves in curved space is that in the B matrix, lapse and shift shows up.
Yes.
And the lapse and shift then also goes into the eigenvectors. So what is here now plus minus 1 will turn into a plus minus alpha plus beta dot n. And so definitely the eigenvalues will depend on the above variables. And I think for the scalar field, even in curved space, the T matrix does not depend on alpha and beta by coincidence. But I think in principle it can.
If you put in the constraint damping terms, it would, for instance. But what I was trying to say was, even for that case, or for generalized harmonic, you still do the same calculation. It's just the matrix has more combinations of the variables in it. But it still is a matrix that maps a vector of the evolved variables into a vector of the characteristic fields. It's just the mapping is no longer a linear transformation. It's a nonlinear transformation if the matrix ends up having combinations of these things in it. Maybe that's the best way to answer it. Does that help answer your question?
Sort of.
Yeah.
Just evaluate those.
Yeah. You take whatever the B is. In this case, it turns out that the eigenvectors end up only having numbers. But if the B has, components of the space-time metric in it, those are some of your evolved variables, then the eigenvectors will too, and that's okay. It's just those would be different eigenvectors that would multiply by these variables. So then your transformation matrix isn't just a constant matrix. It depends on the variables, but you can still do this. And did you have a question? Yes.
So when a characteristic field corresponds to when a characteristic field corresponds to a characteristic speed of value 0, does it mean that there is no information transfer across the boundary?
That's a very good question. If the characteristic speed is 0, does that mean there's no information going across the boundary? Yeah, because like Harold showed earlier, what the characteristic fields are is those are the combination of the variables that in some high frequency limit travel in the direction normal to the boundary as waves. And they travel independently as independent waves with different speeds. And if the wave speed is 0, then there is no wave carrying information across the boundary. If the wave speed is non-zero, then information is either leaving or entering the element across the boundary. So the answer to your question, I would say, is yes.
And 1 means towards the right, -1 means towards the left.
Yes, positive is in the direction of the normal, which I've defined to be to the right here, out of the element. And negative is into the element that we're considering, yes. And yeah, okay. Other questions? Yes.
This is like a continuation of the last day's question. You have got like 5 variables, and in the case of the characteristic fields, you have got like 4 variables, but the J index has to run from 1 and 2, right?
No, the J index still runs from X, Y, and Z. There's only 2 independent components. So if you think about this phi parallel here, the J could be X, Y, or Z if your X, Y, and Z coordinates are not aligned with the boundary. So this thing represents it represents 2 linearly independent components that you could write down of the phi. Phi is a vector, and this represents its component in the plane. And so if the normal vector is along your coordinate axes, then yes, there's only 2 non-zero components of this. But if you rotate your axes, then you can end up getting 3 non-zero components, even though this vector does live in a 2-dimensional plane, because you've just rotated so that the normal vector doesn't point straight out of the plane.
So essentially you've got like a reduction of variables in a way.
No, there's still the same information here. It's just a vector can be split into X, Y, Z components, like you would do in the volume here. This would be like X, Y, and Z. Or if I have a boundary, like say this table is the boundary, then I could, instead of splitting it into X, Y, and Z, I could split it into normal and then whatever 2 directions I want here. Now, if this is Z, then sure, then I only have 2 non-zero components. And if you want to say there's a Z component, it's 0. But what if instead of this being my axes, it's like this? Well, then you will, if this is how I define X, Y, and Z, then the normal component will have 3 non-zero components, and the tangential components of a vector will have 3 non-zero X, Y, and Z coordinates, because I've just not aligned my axes with the boundary. If you start with a vector that's 0, 0, 1, and then rotate your coordinates, you can end up with a vector where all 3 components are non-zero. So this J, in principle, could have all three non-zero components, but only because you don't necessarily have to align your coordinates, your XYZ axes, with the boundary.
So the rotation is on the tangential plane.
So this, what I can say is phi j and j is 0. This is a part of phi, and it is the part of phi that is orthogonal to the normal. Now, that doesn't necessarily mean its XYZ coordinates, which is what J is indexing, are only have two non-zero values. Because, look, if I have a vector parallel to this line here, if my X and Y axes are like this, then sure, it's only got a Y component that's non-zero. But if I use axes like this that are diagonal, then this thing has non-zero X and Y, even though it's living in this plane, because my axes don't align with the plane. Other questions? These are great questions. Thanks for asking. Yes?
So, once you rotate once you rotate the element, so will the external parameters also change? Like the nk external, will it also change or will it remain the same?
So the internal and external is just a way of labeling the element and its neighbor. And here I drew them nice and horizontally, so the normal is horizontal, just to keep this discussion simple. But in practice, you might have a domain like this. And then if this is your element and you're thinking about this boundary, then the boundary itself is at an angle in your x, y coordinates if those are horizontal. So if the boundary itself is at an angle, then the normal vector might have two non-zero components in 2D or three non-zero components in 3D, and so might the tangential vectors. These are two separate parts. This is the tangential part of the vector, this is the normal part. And if you want the total phi j is just the normal component, NL phi L, times the unit normal vector, you might call it n hat, but I'll just call it nj here, plus the part that is orthogonal to that, phi parallel. And you can split it this way, even if your element is on some angle, so this split doesn't correspond to an x, y, or z coordinate split. Does that help make sense? Does that make sense? Okay.
I had like a small question.
Sure.
Just like an element in the Galerkin method.
Yes.
Is in the physical space, it's sort of curved.
Yes.
So the normal component would vary across the domain of the physical component. So is it like ignored?
That's an interesting question. So all of our elements are hexahedral. So even if you have a curved boundary like this, so that, I see what you're saying, so that, yeah, the normal points in different directions, then no, I mean, it points in different, I guess the way I would answer that is you could always avoid that complication by transforming back into the logical frame where they're all cubes. And that's probably how I would try to think about it for right now, anyway. It's a great point, but I think you can always avoid it. This is the physical frame. And the reason I brought the physical frame into the discussion is that is what defines these J axes. And so there was this question about how many J's do you have that are non-zero? That's why I had to bring the physical frame in. But in terms of actually figuring out the normal in the logical frame, the normal points in the same direction throughout the boundary. Okay. So now that I reminded you, and we had some good follow-up discussion answering some questions about the characteristic fields and speeds, and I've written down how to get the characteristic fields and speeds from the scalar wave system, and these all happen to be numbers because the system of equations is fairly simple and the n matrix is fairly simple. In general, you could still do the same thing in a more complicated system where this matrix, instead of numbers, could also have g's and pi's and stuff like that in them, and that's fine. This is still how you would figure out what combination of the variables are traveling waves across a boundary. Now, the reason we need this is because of the question that I wanted to come back to. What boundary condition do we want to impose, and how do we impose it at a boundary like this between two elements? That's what I want to talk about for the rest of the time on the blackboard. So how do we impose a boundary condition? Well, let me remind you about not the principal part of the equations, but the full part of the equations. So if I write the whole equations, dtu alpha plus b I alpha beta partial I u beta minus a source alpha, that's equal to 0. And then we did the whole dg business where we multiplied by a basis function and integrated, and we ended up with the following. We ended up with 0, integrate over the kth element, which I drew on the left over there, integrate over that of partial t u alpha, and you could expand this in spectral functions if you wanted to. I'm not going to do that right now. bi alpha beta partial I u beta minus S alpha. So that whole thing, then we added a surface integral to it, d alpha. And both of these are multiplied by some basis functions. And phi I, the I breathe index just labels which basis function you have. I haven't said what they are, they're just functions of space. If there's time before I get to my slides at the last minute, then I'll go ahead, for the last part of the lecture, I'll go ahead and say something about what these phi's might be in 3 dimensions. But for now, just think of it as some function of space. What I want to tell you is, what is this d alpha? D alpha is a term in a surface integral that is designed to be there to enforce the boundary condition that we want to enforce. Now, the boundary condition that we want to impose here is a reasonable sounding idea. What we want is a conservation of flow of stuff or information. That doesn't sound very precise, but I can make it mathematically precise. What we want is any information leaving the element had better enter its neighbor, and any information leaving the neighbor had better enter its element. In other words, nothing disappears through the boundary. But what do I mean by information and nothing? What I mean is, if you take high frequency waves made of these combinations of the variables called the characteristic fields, those things that travel independently at whatever speed across the boundary one way or the other, if you take those traveling waves, then what we want is that whatever is flowing out of one side of the boundary had better be flowing into the other. Now, not all of these characteristic fields will have speeds flowing across the boundary. Some might have 0 speed. Some might have speeds that are going in. Some might have speeds that are going out. For element omega k, only the characteristic fields whose speeds are coming into the element need a boundary condition. Think of it this way. If I'm simulating a box on a computer and stuff leaves the box, that's fine. The computer can just say, okay, I'm not going to track that particle anymore. It left. I don't need something to control it. But if you have particles coming into the box from outside the part you're simulating, then you need a boundary condition to say, hey, how did something get into this box when the box is all I've got? So when the computer simulates these elements, it distributes them over all these cores. And you can think of this element as just sitting there by itself. You're doing the time stepping, runga kutta, like Harold said, or something like that. And then every time you want to know what's happening on the boundary, that's when you need to know what's going on with your neighbor. Your neighbor might be sending some propagating waves in the sense of these characteristic fields coming into the element. And that's where communication would happen between the elements. Yes?
So, like you told that we have to count for like the information leaving our element.
That's right.
So, like, for example, if it is leaving in the other direction, like we have taken an external this side, but what if information is leaving the other way around, and how do we account for that?
Mm-hmm. So basically, in the system that I've described, we're using hexahedral meshes, which means in the logical frame, each element is a cube, so it will have 6 neighbors, and you will need to do this process for all 6 boundaries. And what matters on any of those 6 boundaries is the inward direction. Imagine this table is your element. If you have some combination of the fields that I'll represent as just a little object, or my hand, like a traveling wave, if it leaves, you don't need a boundary condition. You can just say it leaves and doesn't come back. But if something comes in, then you need a condition to control it. So the thing that we need to put a condition on are the characteristic fields with incoming speeds. Outgoing speeds can just be allowed to leave, but incoming speeds, we've got to say what's coming in, since this element isn't simulating that. Yes?
We are concentrating on the outgoing things, right? So we are saying, okay, so it will not affect the boundary conditions, but when something leaves the system, so it will affect the system, right? So hence it will sort of change the conditions in the thing. I mean,
I'm sorry, can you ask that again?
so we're not concentrating on the outgoing waves, right? We are saying outgoing waves, they will not affect the boundary conditions.
Okay, yeah, what we're saying is that outgoing characteristic fields, so not any wave, like a gravitational wave in a GR simulation, isn't necessarily going to just pass right through the boundary, but because it might not consist of only outgoing characteristic fields. It's the characteristics, those special combinations of the variables, and those might not correspond to the combination you would need to get, say, the gravitational wave strain. So don't think like a physical wave exactly. These are just combinations of the variables we're solving for that travel as waves in the computational domain.
So my question is that, so this variables will not affect the actual physical system that we're trying to describe. So is it?
For the system we're trying to understand, it's true to say that the characteristic fields with speeds going out of the element will not affect the future of that element. To get to the next time step, what you need to know is what's coming in from your neighbors. What's going out will affect your neighbors because it's going into them, but it won't affect you.
Okay.
And in fact, that brings us to the next idea. What I want to say is, what kind of boundary condition do you want? And you want to say that whatever incoming characteristic field, whatever fields have incoming characteristic speeds into the element you care about, those incoming characteristic fields had better be equal to the outgoing characteristic field on the other side of the boundary. So the flow of the characteristic fields is what you require to be continuous across the boundary, or you would like to be, in the limit of infinite resolution anyway, continuous across the boundary. So how can we make that happen? Well, the characteristics fields, I've written down some notation, those are just called W alpha. Now, what I'm going to do is write down W alpha hat. These are the characteristic fields. And now we would like to make a new vector that isn't just the set of characteristic fields, but is only the fields with incoming speeds. So it's only the fields that are incoming into an element. So the thing I'm going to multiply this by will be different for each different element. But for the particular element that we're thinking about, then I can multiply this by a matrix I'm going to call capital lambda minus, actually I'm going to call this W beta hat. And I'll call this alpha hat, beta hat. So this lambda minus, what is it? It's a diagonal matrix whose values are 0 for each field whose characteristics are 0 or positive, and is the characteristic speed itself for any characteristic fields whose speeds are negative. So just as an example, in the scalar wave case, we have 4 characteristic speeds, but only one of those speeds is negative. Now, it so happens in this system, the speeds are just constants. They don't depend on where you are like you would in a more complicated situation. So that means that if I take this vector and multiply it by a diagonal matrix that has the characteristic speeds if they're negative or zeros otherwise, then this, for the scalar wave system, you can figure out what it is. It would just be 0, because that doesn't have a negative speed. The G doesn't. The phi parallel doesn't. The pi plus NL phi L doesn't. And then the last one has would just get a -1, because this matrix would just be equal to a diagonal matrix 0, 0, 0, and then the negative characteristic speed survives. So this matrix is kind of like the identity matrix, but you set even the diagonals to 0 unless the characteristic speed is negative. If it is negative, you put the negative characteristic speed in. So we're weighting the characteristic fields. And in this case, only one of them is incoming. So that one, this thing for the scalar wave would turn into minus pi minus NL phi L, minus the normal component of phi. So this one survives, the rest are zeros. This is the one we have to put a boundary condition on because it's the one with the negative characteristic speed. Okay, so what boundary condition do we want to put on this? Well, one thing you might want to say, wanted to try to say, is that this is continuous across the boundary, that whatever leaves this element, leaves the neighbor, enters the element. And since these normals point in the same direction, in both cases, you want the negative characteristic speeds. In this element, the negative speeds, the ones opposite the normal vector, coming into this element. In the neighbor, the negative characteristic speeds are the ones leaving the element and going into its neighbor. So in both cases, it's the negative characteristic speeds that you want. So what you could try to say is something like this. Lambda minus alpha hat, beta hat, W beta hat on the element itself. So I'll give these interior superscripts, lambda minus interior. You could try to say that that's equal to lambda the negative, this only keeps the ones with negative characteristic speeds from the neighbor. Exterior alpha hat, beta hat, characteristic speeds, characteristic fields, beta hat. Now, that expresses the idea that what leaves one element enters the other element. Now, there's just one problem with this boundary condition. This is all written in terms of the characteristic variables, but we would prefer to have something in terms not with an alpha hat index, but with an alpha index, one that depends on the variables, not the evolved variables. We want a boundary condition on the things we're solving for, g, pi, and phi, not on these combinations. So you can fix that by just hitting each of these with that T matrix, T, alpha hat alpha, alpha alpha hat here, alpha alpha hat here. And what this does is this says, okay, if I then turn this weighted set of characteristic fields back into evolved variables using this T matrix, which I wrote for the scalar wave system here, and do the same thing over here, these should all say from the neighbor, then those had better be the same. So if they're the same, then you can subtract them and say you would like this to be 0. And in fact, that's what we do. And we call this d alpha. Except for a minus sign. We call this minus d alpha. So we'll just subtract them the other way. It doesn't matter. You want it to be 0, but we'll subtract them the other way. So this is d alpha. And by putting d alpha into this surface integral here, that is how we impose this boundary condition that says that the information in terms of the characteristic fields leaving an element are the same as the information entering the neighbor. And you can kind of see here that this has the properties that I said earlier d alpha should have. In the limit of infinite resolution, the values of the variables and therefore their characteristic fields on either side of the boundary will be continuous. They're only discontinuous because of numerical error. And if you drive that to 0, it becomes continuous. And so if x equals int, if exterior equals interior, then d alpha isn't even there. It's just 0 because I just replace all these x with ints and now I've got the thing minus itself. So that's good. Yes.
The second T also be
Should the second t also be what? No, these three terms are for the.
The idea was that characteristic fields leaving one domain
Yeah.
should be the same as fields entering the other.
The idea was that the incoming fields weighted by their characteristic speeds, so take W beta hat and hit it with this matrix to weight it by the incoming char speeds and set all the outgoing ones to 0, that this should be the same on either side. And then we hit both sides with the appropriate way to convert them back into evolved variables instead of characteristic variables for that side of the boundary. So on this side, you would convert the variables back into evolved variables with T exterior. On this side, you would convert them back with T interior.
Mathematically, the equation which holds is without me, like which should hold is without me, because that is the equality of the characteristic.
Yeah, yeah. So
you want to simply convert it into physical variables because that's what we have.
yes.
So shouldn't you multiply both sides by the same matrix? Because in our case, it's a constant, so it's fine.
Okay, so in the limit of infinite resolution, it's all the same anyway, and then yes. Numerically, that's not what you want to do. Everything that you do in this side of the element, on this side of the boundary, has to be done with the stuff in that boundary. At least that's what we choose to do in this numerical scheme. You could try other things, but this is the recipe that has the properties that we want. If you don't have but this be exterior and this interior, then this isn't a suitable choice for d alpha, because we need swapping interior and exterior to only change d alpha by a sign, and that wouldn't be the case if this one was also an interior. So I get what you're saying, like algebraically, if you just take this thing and try to multiply it by something, they'd have to be the same. But I'm trying to just motivate why we're constructing a boundary condition that preserves information flow across boundaries, but also has these properties that earlier in the week I said this d alpha has to have. One of them that it has to have is that if you switch exterior and interior, it should only change by a sign. And so numerically, that's what you're doing. There's lots of things we've done like this, like adding this flux term at all. This isn't true in the limit of infinite resolution. This is just some numerical thing we're putting in to control what's happening across these boundaries. In the limit that you're solving the real thing with infinite resolution, this d isn't even needed because everything is continuous across the boundary. So the deal with interior and exterior is numerical. It's dealing with numerical error. So I don't know if that helps explain why I'm doing it this way, but there's no way, if we did it the algebraically obvious way, I guess, where we're doing both our interiors, then this would not be a good choice for d alpha for us because it wouldn't have this property that we wanted it to have. And this property turns out to be, this turns out to be important numerically, but I don't have a good thing I can explain why in this lecture right now. Okay, so I think that's most of what I wanted to say. You could imagine figuring out what this actually is going to be. I've shown you what part of this is, and then you could imagine just trying to convert this back into physical, into the evolved variables. And if you do that, then what you would have to do is you would have to take this whole thing and multiply it by t. Now, in this case, t is a constant. So for the scalar wave, it actually doesn't even matter for the t's whether you're evaluating on the interior or exterior because they're constants. But in general, it matters. So what I need to do is take this t, which is 1, 0, 0, 0. I should have left more room. 0, 0, 1/2, 1/2, 0, 0, 1/2 minus 1/2, 0, 1, 0, 0. And I need to multiply that by the by this 0, 0, 0 minus pi plus normal phi. Okay. And so what you'll end up getting is you'll end up getting, so you'll end up getting what terms will even survive. Let's see. So this will be equal to 0, 0, 0, 0. First term is 0. 0, 0, 0, 1/2 of this. So minus 1/2 pi. Oh, wait. 0, 0, 0. So it's positive 1/2 times minus pi plus NL phi L. And then the next one's going to be 0, 0, 0 minus 1/2 times minus pi plus NL phi L. And then the bottom one is 0. So what this is saying is for the scalar wave system, remember the evolved variables, which I wrote over there, are g, pi, the normal part of phi, and the tangential part of phi. So pi, for the pi equation, you have to impose, pick up a term in d alpha, which means you pick up a boundary condition involving one of the characteristic fields, pi minus the normal of phi. And you pick up a term with the opposite sign for the normal part of phi. And the other parts of phi and g don't pick up anything. And that has to do with the fact that they are characteristic fields with 0 speed. So there's no information flow. And it turns out, if you were to go to the SpectraCode website and look up our implementation of the scalar wave system in flat space and set to 0 some things I've ignored, like the velocity, like they allow the velocity, like they allow the grid to be moving, which introduces some corrections I've ignored here. The grid might move, for instance, if you have 2 black holes tracking each other, but whatever. Even in the scalar wave, they'll allow the grid to move, but if you ignore that and you ignore all these constraint damping terms so that you just have the exact same system as us, this is exactly the value of d alpha that we use. It's sometimes this is called an upwind or upwind penalty choice. But that is what we plug in for the d alpha. And I tried to explain why in terms of characteristic fields, but I also chose it so that it has this symmetry, interior and exterior. This is the more precise version of what goes in, what leaves one comes out the other that I want to enforce. Now I explained it in the characteristic space, but I actually wanted to impose this swapping interior and exterior in the physical space or the evolved variable space, not in the characteristic space. So that's what I wanted to say about the boundary conditions, or the boundary correction, the non-conservative boundary correction, d alpha. And you'll also notice that if interior equals exterior, oh, I think I said that already, then it just goes to 0, like we wanted. Any questions about the boundary conditions? Yes.
In the d alpha equation, so does that mean that the conservation of information that is traveling from one block to the other, so it depends upon the accuracy of the grid points that we are considering? So is it something like that, the conservation of information?
Yeah, so conservation of information is kind of a heuristic to motivate using this. In real life, you just want to use something that doesn't create errors that are blowing up. And it turns out conserving information in the sense of the characteristic fields weighted by their speeds, but converted back into the evolved variables, that's the thing that you need to keep the same across the boundary. Now, in terms, does this depend on resolution? Absolutely. There's the whole reason there's a difference between the neighbor, I mean, there's the neighbor, but we're really evaluating things on the neighbor's boundary and then saying what's happening and on the element's boundary. And these boundaries really are touching each other. I drew them separately because in discontinuous Galerkin, when you have finite resolution, they can disagree. But in the limit of infinite resolution, they don't. So the whole existence of this term is a consequence of limited accuracy. Other questions? If not, I have just a quick aside before I go to slides for the last 20 minutes or so and show you some results of DG. There's been some questions that have come up from time to time about the basis functions, about these phi sub i's. Now, you saw in Harold's classes in one dimension of space what those could be. They could be orthogonal polynomials. And I just want to say something real quick about what they might be in 3 dimensions. So I'm not going to go into detail about the different kind of polynomials that we use, but I want to say at least a little something about, so I'm going to make some room here for this, right in the middle here. I want to say a little something about how we actually do these expansions in more than one dimension. Because so far I've been treating all this kind of abstractly, where I just say, oh, there's some basis function, phi sub I, it depends on space, x, y, and z. But how? How do you choose it? We still like orthogonal polynomials, but those are one-dimensional functions. How do we do this in 3 dimensions? And I'm just going to say a little bit about how you can do that. In 1 dimension, I'm going to make the summations explicit for a minute, then I'll go back to the summation notation. I breathe equals 0 to some finite amount of terms n, and then here's the spectral coefficients times your favorite orthogonal polynomial, and that depends on the a logical coordinate. So in 1 dimension, maybe you've got a domain that goes from -1 to 1, where your favorite polynomials are defined, and then you can expand any functions between -1 and 1 u alpha. You can expand those in terms of that. So I guess I should have written the dependence more explicitly. U sub alpha of x. In 1 dimension, x is the physical coordinate, psi is the logical coordinate. I guess I should draw the map again. I've got some room here. So we've got some deformed x cube with x, y, and z coming out of the board. And then that turns into some logical cube where you've got psi, eta, and then zeta will come out of the board. So the issue is the orthogonal polynomials are defined here. So for now, I'm going to be thinking about dealing with things in the not deformed cube space, the logical space. Logical. Okay. Not the physical space. There's not enough room. I'm not going to label it. So how do you generalize this to 3D? Well, you can sort of do, there's sort of a natural thing you could want to try. Well, let's just use a polynomial for each dimension. So let's have a triple sum, I equals 0 to n. And let's assume for now we're using the same resolution in each one of these sums, but you don't have to, but we'll just do that for now. K breathe equals 0 to n. And now we'll have a spectral coefficient that has 3 indices on it, times pi of psi, pj of eta, pk of zeta. So this is what you would do to expand u alpha in 3 dimensions, where I'll make the equals point down here so I have some room. U alpha of, say, x, y, and z. It's equal to a triple sum. And each of these is an orthogonal polynomial. They could be Legendre polynomials, they could be Chebyshev polynomials, or whatever. Now that's okay. That doesn't break anything that we did before, because you can just come up with some numbering scheme to relabel all of these polynomials. Like for instance, you could say I equals 0. You could say I breathe, j breathe, k breathe equals 0, 0, 0. We'll call that basis function number 0. I, j, k breathe equals 1, 0, 0. We'll call that basis function 1, and so on. So you're free to take to just call this product your basis function and just give it a serial number, just number them in some order. Now the total n would be different. Up here, if you're just numbering them with a single index, the actual numerical value of what I was calling capital N would be different, but it's just a matter of labeling. So all this derivation where I said there's just phi i's and this goes from 0 to some finite number, that still goes through. It's just that finite number is going to be bigger if you've actually got, if you've actually got 3 separate things, like it would be n cubed in this case, right? So that's just a little follow-up, because I know there were some questions about that. And then if you wanted to do the mass matrix integral, I'm going to make a little more space here. We worked all that out, so I think I can free up some space here. So if you want to do the mass matrix turns out to be, I'll get rid of this. So we've got phi, not capital Phi's. The mass matrix that we derived the other day was just this integral d cubed x of phi I breve phi j breve. And so in reality, when these things are allowed to depend on several different, and so this was called Mij. So if actually you want to renumber these and say, well, actually, I'm going to think of these i's instead of going like 0, 1, 2, I'll triple label each one. Then you can write down a mass matrix Mij k for the first index there, and then L, M, N for the second one. And then that would be equal to integral d cubed x of phi I j k, if you like. And you could rewrite that as, because phi ijk here is just a product of 3 things. So that could be like an orthogonal polynomial I of psi, j of zeta, of eta, k of zeta. That's a terrible zeta. And then you've got 3 more, L, M, and N of zeta, eta, and psi. So the idea is this mass matrix would then turn into an integral of a product of 6 of these polynomials if you're in 3D. But this is a volume integral. I could rewrite the volume integral. I'm just going to call this stuff square brackets. And you could rewrite it as integral d psi from -1 to 1, d eta from -1 to 1, d zeta from -1 to 1 of a determinant of a Jacobian matrix that comes from the difference between the physical coordinates and the logical coordinates psi times the stuff in square brackets. And then many of these functions only depend on one of these variables, so you can move them through some of the integrals, and eventually you'll end up doing several, one-dimensional integrals. But only if this Jacobian is a constant and slides out of the integrals do you end up getting, if I have 2 of these functions that are orthogonal, like say I is 1 and j is 2, only then would you get 0, because otherwise this Jacobian breaks the orthogonality conditions, potentially, if it depends on space. Then you don't just have the integral of, say, P1 times P2, you would have P, like say I was 1 and L was 2. You don't just have a psi integral of those 2 functions, you have it times some other function in space, which would spoil the orthogonality. So that's just a quick follow-up, since there was some question about how does this actually work in 3D. Any questions about that? If not, then I'd like to switch to the computer for the last part of the talk and show you some results that we've been able to get with our discontinuous Galerkin task-based parallel code, Spectre, for binary black holes so far. It's still a work in progress. We don't have complete simulations, but I want to give you a status update of where we're at. So I'm sharing my screen for everybody on Zoom. So what's the status of binary black holes in Spectre? So we are currently able to do our first in-spirals with 2 black holes. And this turns out to be complicated all by itself. Besides all the formalism that I've introduced this week, if you have 2 black holes have singularities in them. And that means that you have to remove that part of the grid. So the kind of domain that we're actually going to have to evolve these on is going to have a shape something like this with two holes in it. And constructing a shape with two holes cut out, a sphere with two holes cut out of the middle, out of cubes, it can be done, but it takes some work. And that was one thing that took a lot of work for the developers building this code. Marceline Bonilla, who's a postdoc at Cal State Fullerton, where I'm at, managed to do that. But that was like a big chunk of a PhD thesis to construct a good version of this. So there's that. And then if the black holes orbit each other, those holes had better track the black holes as they move. So you have to have this move somehow in response to what the black holes are doing. Like you need to rotate the grid around as the black holes orbit, and you need to deform it as the black holes approach each other. This requires something like a thermostat, or more formally, a control system, something that monitors where the black holes are and applies some time-dependent coordinate mapping to not just deform the cubes from the logical frame, like I was showing over on the board over there, but to get them to spin around. So with that aside, let me show you a movie of something we've been able to do so far. This was made by one of my students at Cal State Fullerton. And let me start it over again. There was a little bit of lag there. I don't know if it's going to work better the second time or not. Let's see. Yeah, maybe it's worse. So what this is showing, these are the two black hole horizons. They're supposed to be going around each other. Maybe the whole internet's not so good right now. And then if you zoom out, you can see some gravitational waves coming out. Just wanted it to look a little smoother, but that's the Wi-Fi. And what we've been able to do is do the first comparison of just the beginning part of the simulation with Spectre and Spec to start, because we would like to make sure that the new code is agreeing with the one we've been using for 10 years, or more than 10 years now, I suppose. I'll try playing it one more time and then I'll give up. Oh, well, the frame rate's not great, but at least you kind of get the idea. And as the black holes orbit, they send out gravitational waves. So, okay, so here is a comparison. So what I'm showing on this plot are two curves. This is a measure of the gravitational waves calculated from the simulation, except the simulation wasn't so jerky as the movie looked. These are just the leading order quadrupolar part of the gravitational waves. So L equals M equals 2. And anyone who's in the know with the technical details, I'm plotting here the Newman-Penrose scalar psi4. That's actually the second time derivative of the stretching and squeezing of the strain that I showed you in my slides on Monday. And this stuff at the beginning is a spurious, unphysical burst of waves called junk radiation. All numerical relativity calculations have this. You might have talked about it last week. I don't know. It comes from us not knowing exactly the correct way to construct initial data that satisfies the constraint equations, like the Ci in the scalar wave, and that also has two black holes in equilibrium orbiting each other. The initial data that we construct is always perturbed a bit, and when it rings down, it makes a high frequency burst of gravitational waves, but then it settles down to the physical thing. Now, there's also, if you squint, you might be able to see the thinner curve here. The thinner curve lying underneath is from a spec simulation. So these two curves were on top of each other the whole time. Now, that's reassuring from sort of a qualitative point of view, but that's not really good enough for a numerical relativist. Just because they look close like this, you want to know how different are they? So what I want to do is I want to show you how different in amplitude, you can sort of see the wrapper of this wave in amplitude, and how different they are in phase. And I'll do that by subtracting them, so you can actually see the differences and not just say, oh, they're kind of close because they look like they're on top of each other. Okay, so maybe this curve will be easier to see. There are two polarizations of gravitational waves. I just showed the real part, which is one polarization, and here's the other. And it does the same thing. The thick curve from Spectre is right on top of the thin curve from Spec, but the Spectre simulation was shorter, and then you can just see the Spec simulation continue on. Now, let me show you some differences. Oh, and there's the amplitude, and that agrees very well as well. So I'm going to show you differences in this amplitude between the two simulations. So here's the plot of the gravitational waves, and now maybe that's just a little easier to see than the smaller version on the previous slide. and the curves are all on top of each other, sure, but how well do they agree with each other? Okay, so what I'm showing here, this is amplitude. And what I'm showing on the left are just the amplitudes. There's a burst of unphysical amplitude, and then they settle down, and the spec simulation is pink, the spectra simulation is cyan, and sorry, it's not showing up better on the background here on the projector, but they're on top of each other. But the important thing is this yellow curve, which is the difference. So what I'm showing here is the fractional difference of these amplitudes. Now, at the beginning, when there's all this high frequency junk, numerical relativity simulations normally don't resolve things very well. So it's not surprising that there's no good agreement here. There isn't between spec and spectre. Their junk radiation is different, but that's also not a physical interest. After things settle down, this and the junk radiation is gone, starting around here, this is where you would want to start thinking about how accurate the physical part of your waves are, the part that you would use for some gravitational wave application. And right now, these two simulations agreed to within about 1% in their amplitudes, this 10 to the minus 2 level here. So that's reassuring that this completely new code with completely different methods, if you take the leading order gravitational waves from both codes and just plot them on top of each other and subtract them, that you get about a 1% difference in the amplitudes after the junk radiation is gone. You can do the same thing with the phase, but there's an extra step. The junk radiation often, this burst of radiation often gives an unphysical phase shift as well. So what I did here is I made the wave phases agree at the final time that I had for both simulations. So it's 0 at this time. And then I wanted to find out how much did that phase difference grow back until the junk radiation made the waves totally different. And that ended up being sort of tenths of a radian of phase. And that's, not as accurate as we want spectra to be, but for a first cut, saying that these are within tenths of a radian is it's not like the absolute best accuracy that any code can get today, but it's not terrible for a code today. So that gives you an idea of if you just subtract those two phases that are on top of each other, you can't see them well over here, but when you subtract the wave phases, you get something, sort of tenths of a radian.
Yes, so I have a question.
Yes.
Yeah, so these are for non-spinning systems.
Oh yeah, I should have clarified that. The system that we've evolved to test the code first is equal mass, zero spin. We are working right now on the first attempts to add unequal masses and spins that introduces extra complexity to the control systems I mentioned that have to keep the grids tracking the black hole horizons. So we always do the equal mass non-spinning first because it's easier.
And
yes.
By spinning, you mean aligned spins only?
Yeah, we're not trying processing spins yet. That would come later too. We start simple and then gradually layer things on. But we haven't yet gotten those things working in the new code. Spec can do all those things, but Spectre, we haven't yet tried that.
And what do you think, what is the reason behind this difference in phase between spectra and spec? Is it because we're only considering the dominant mode, or if you include more and more higher modes, so will it improve? Or,
yeah, that's a good question too. So I'm not showing it on the plots here, but I also ran several different resolutions. And basically the size of these differences are comparable to the sizes of differences between resolutions within the individual simulations. So I think what's limiting you here is the numerical accuracy of the two simulations. But I haven't shown that on the plot here. This is just giving you a feel for how big the differences are. But that's what I think is causing the difference. There could be they are starting from the same initial data. So it's just how they were evolved with their numerical resolutions. And I tried to do some comparable resolutions, but one simulation is more accurate than the other just by the way you set up your grids.
So the difference is only due to the algorithm that both the codes use, right? I mean,
well, they're using different algorithms, yes, but any differences should only be because of differences in resolution, not differences in algorithms. Both algorithms, if you implement them correctly, should give you the same result when you've got a grid that gives you the same accuracy and are using time step sizes that are the same, give you the same accuracy and so on. But you're getting at something really interesting, which is making such a comparison precise is hard because there's a lot of things that are different besides the algorithms. There's the time stepping, there's choices in what kind of time steps you take. that these algorithms make in different ways. The spatial grids are totally different. So you can't just say, I'm going to run these on the same grid. You have to run them on different grids and then try to pick grids that are similarly accurate. So that's a very good point. Yeah. And then one last thing I can show you is the mass of the black holes. This is the difference in the mass of one of the black holes from 0.5. We just set in our units, each black hole has a mass of 0.5 initially, so the final mass is 1. And these numbers are just pretty small, like 10 to the minus 5 or so. And if you look at differences, yeah, somewhere some number times 10 to the minus 5 is what the difference is after the black holes have settled down. And even during the junk radiation, the black hole masses agree very well. Let me show you a little bit about the grids. We've talked about discontinuous Galerkin so much. I wanted to show you some pictures of what this looks like for real. So how do you interpret this picture? So each intersection of grid points is a collocation point. This is one of those grid points that turns out to be equivalent to knowing the values of the spectral coefficients. The way we construct our grids is, like I said, you can see there's a hole here and there's a hole here. The singularities of the black holes are in there. We had to cut the singularities out of the grid. In finite differencing, you can do a puncture approach where you can just turn off individual grid points if the puncture gets too close. But here, because we're doing spectral expansions, you can't just like turn off a coefficient in a spectral expansion and only affect one little region. You would affect the whole element if you did that. So instead, we have to do this excision idea where you remove the singularities. And then you can kind of see here some elements. You see this shape here? This is that deformed cube shape that I've been kind of sketching on the board. And here's a bigger one here. And you can sort of see each of these little, so this might be an element with a bunch of grid points inside it, this thing right here. Is just one of these deformed cubes. And I'm showing a cross section, but you've got to imagine these are put together into a sphere surrounding each of the black holes. Now, this is not the entire grid. This is just zooming in to show you a problem that makes this more complicated than the simple little, like I was drawing grids like this when I sketched them on the board, just the part you would put around one black hole. But if you have a sphere with two spheres cut out in the middle and you want to cover that with cubes, that's hard. And the way we do it in Spectre currently is something like this, where each sphere surrounding the individual black holes is surrounded by some deformed cubes that end up making an overall brick shape around them. And then if I zoom out, outside that, that is what I was showing you on the other slide, that brick shape, then that's surrounded by some deformed cubes that start out cube-shaped and gradually become spherical again. And then if you zoom all the way out, then you've just got some large spheres out here, and this is where the gravitational waves are going out to the outer boundary. Out here is where you would impose a boundary condition to say what characteristic fields with incoming speeds are doing on the outer boundary. So that just is to give you a feel of what these deformed cubes really look like in practice. For a simulation with two black holes, it actually is kind of more interesting than just the simple little grids I was trying to sketch on the board that were just like, those were just one part of this. I can show you some differences that choosing the grids makes. So here's a plot that shows constraints. I'll say something about the yellow curve, what's the deal with the yellow curve and green curves in a second, but this white curve lays out the cubes like this. So each element started out as a logical cube, and there was some coordinate map that converted the logical coordinates psi, eta, and zeta into x, y, and z. I'm going to change it. This map is called no equiangular in the plot. Now look at this. Do you see the difference? This is not equiangular. This is equiangular. This version spaces the grid points in the angular direction more evenly. And this is just a choice of how we're mapping our logical cubes into these deformed cubes. It doesn't look like a huge difference, but this is a measure of the constraints or of the numerical error of the simulation versus simulated time. The white curve is this. And the same exact simulation where the only thing I changed was this mapping here is the yellow curve. Now, something funny happened here that had to do with the outer boundary being small. But if you do the same exact thing but make the outer boundary twice as big, you get the same increase in accuracy, but then you don't get this weird feature. So the point is, just a tiny change in how you've constructed this mapping from the logical cube out to the real physical domain can make a difference for the same number of grid points of more than an order of magnitude in your accuracy. This really drives home something that Harold was showing repeatedly in one dimension this week, that properly choosing what basis functions to use and how to arrange them to capture the underlying physics can have big effects on the accuracy. And if you choose it wrong, then you'll be wasting a lot of computational power to try to get to the same accuracy. Or maybe it's not even possible with a sufficiently bad choice.
Yeah, so
yes.
So in the x-axis, what is that coordinates?
Are you asking
time? Yeah,
the yellow curves?
So the time axis, you written coordinates, so what that corresponds to?
Oh, yeah. I can say something about what the code units are. So in the units we use in the code, first we set G and C to 1, so geometrized units. Then we set the initial mass of each black hole to 1/2, so the total initial mass is 1. And this is showing time in units of the total initial mass of the black holes.
Okay.
So that's what I meant by code units. I just said code units because I didn't want to get into it unless someone asked, but since you asked, I'm happy to say that's how we do it.
Okay, and also, as the plot says, if you increase the value of R, the error reduces, right? So
Yeah.
you've taken 300 and then went on to 600. So is there a lower bound or upper bound between taking the radius?
So it turns out that moving the outer boundary out helped with whatever numerical instability this was. I'm not sure exactly what caused this, but something that I don't have on my slide, there's a technique called filtering that actually cures this kind of thing, regardless, and so that you don't have to, without having to worry about, okay, did I put my boundary far enough out? Filtering is the idea where you set this n to be a little bigger than what you actually want for your resolution, and then you repeatedly zero the top mode, say. So like the top one of these, you take a step and it gets updated, but then you set it back to 0 and don't let it grow. So that also can help cure this kind of thing. The last thing I want to show you is very new. Just before I left, the week before I left, I got a video from Kyle Nelly, a grad student at Caltech, who has been working on, who has been taking charge of the part of our code that's the control system that deforms the grid to follow the black holes. It turns out that part is crucial in moving beyond two black holes that are near each other to actually letting them merge into one big black hole when you do this excision approach. And just last week, we have our first result here. This is going to look jerky like the other movie probably, but these are two horizons of two black holes. All right, let me play it again. And we, for the first time, were able to get those black holes starting from rest. So this is simplified. They're not orbiting each other. We just let them go from rest, and they fell together, and we were able to continue the simulation far enough that the black holes merged, and then a common horizon formed around them. And that's the first time the Spectre code, after, 5 years of development from the ground up, was able to get a merged black hole. In admittedly a very simplified case of no spins, equal masses, and they're not even orbiting. We just let them go from rest. So they crashed right into each other. But that's easier than doing the in-spiral problem. Basically, we needed some fancier deformations of the grid that were only just starting, or to the control system deforming the grid that we're only just starting to add now to allow the black holes to merge. That part of the code is exactly the same as in spec. And we know what to do, we just haven't implemented it yet because we did it in spec as well. Yes?
I see no deformation of the individual horizons.
Thank you for asking about that. They do deform, but in the coordinates we're using, if you're just showing the shape, the coordinate shape of the black hole horizon, it doesn't look that non-spherical. But it's a bit of an illusion in some ways because just these black spheres, those are not frame-independent quantities. Those are just in our coordinates, where did the horizon happen to be. If you want to know if the horizons are deformed, you can compute the two-dimensional Ricci scalar intrinsic to the horizon. And if you look at that in this simulation, they are actually deformed, as you would expect. It just, in these coordinates, you don't actually see a measurable deformation. And in fact, the deformation isn't huge. It's like a small perturbation until they're very close to each other, but they are deformed. It's just not shown in this movie. That's a great question. Thanks for asking about that. So that's what I wanted to say. Does anybody have any other questions? Yes.
Can you go back to the slide where the grades is maximum
Maximum zoomed in, coming right up.
So here the grids get broader when we are going outwards, but then it suddenly gets really defined very size where.
You mean like between here and here? Yeah. So first of all, I'm not claiming that this is the absolute optimal grid. This was made by some trial and error to try to reduce our error measures in some simulations. You want the grid, because things fall off as 1/r, you need a lot more resolution here than here. But something funny happens when you have to go in a very short space from something, deformed cubes making a sphere, to deformed cubes making a cube, and that is very hard to resolve. And it turns out that, now I'm not saying this is optimal, but the reason we put more points here is because going from this spherical shape onto a cube shape over this distance isn't easy. So there's some logic to why we've got, why that makes a difference, but I'm not claiming that this is the absolute right thing to do. It's just the one we happen to settle on for our first tests. Other questions? Yes.
Like you said, in the code units, the masses of the black holes, we consider it to be half.
Yes.
But the thing is, obviously the masses may slightly differ. So isn't that going to cause some anomalies in the final simulation?
Yeah, so the question is, if the masses aren't exactly equal, doesn't that slightly affect the final result? Yes, it does. In this case, the masses are equal to many more digits than our numerical accuracy. So we're actually limited by other effects. But if we had more accuracy, then you're right. We would have to be very careful to adjust our initial data to make sure that if we said it was equal mass, it really was equal to our numerical accuracy. But we're not so accurate in everything else that that's what we're worrying about right now. But you're right. That's a nice point. Other questions? Yes.
I have the similar question. Like you shown the phase and amplitude differences due to different time stepping and so on. So that was for the equal mass case. But if the mass ratios are different, then the length scales are involved will be different, and we will get the worsening of.
Yeah, that's an interesting question. What happens to the time steps if the black holes are different? In our old code spec, the time step is the same everywhere. So everywhere you take a step, it's the same for every element. And that means the time step is just set by the smaller black hole. I didn't go into this, but in our new code, different elements are allowed to take different sized time steps. Right. So yes, the elements around the smaller black hole would take lots of tiny time steps, while the other elements farther away that had lower resolution could take bigger steps. And then what you can do is you can put more of those lower resolution elements on a core and fewer of those higher resolution elements near the small black hole to try to balance out the load.
So in that case, the differences in phase and amplitude will remain same, even if the masses.
We haven't done that, the unequal mass case yet. So I'm not saying that the plots would come out just like this. You would have to do the simulation to find out how accurate it was. In principle, we ought to be able to resolve it, but at greater computational cost. We're still optimizing the code. It's not yet performing as fast as we think it can. In theory, we tried to make it work before we tried to optimize it. Other questions?
So, like in BSSN formalism, we have constant equations and evaluation equations. So, constant equations give us the initial data and the evaluation.
Correct.
Similarly, this uses the generalized harmonic formalism.
Yeah, so similarly, we're using a different formulation, generalized harmonic, but the initial data, we use a formulation called the extended conformal thin sandwich approach, and that one also solves the Hamiltonian momentum constraints, as well as it borrows an evolution equation to give you a fifth elliptic equation to solve, and that also solves the constraints. So the initial data is made by solving the constraints as an elliptic problem, and then you evolve it using the generalized harmonic symmetric hyperbolic equations.
So what quantity defines the initial data? Like we have the conformal factor in cases.
Yeah, so in extended conformal and thin sandwich, the variables are a conformal factor, and then you actually solve for the lapse and shift to end up specifying your gauge choice after assuming some quasi-equilibrium conditions where you set some time derivatives to 0. Other questions? Well, actually, I think I'm out of time, so I'm happy to answer other questions afterwards. But I think maybe I can take one more quick question, and then I'll answer questions afterwards.
So here we have like towards the center, we have this like one type of elements, and then towards where the grid points become more square, we have another set of elements. So do you use two different set of formulations to calculate it?
That's a good question. Do we use different formulations in here than out here?
Yes.
And the answer is no, in several different senses. We use the same equations. We use the same boundary conditions. We use the same DG formulation. The only thing that's different is, remember, to go from here to here is some choice of a map xi as a function of psi I. How do you go from the unit cube to the grid? That's the only difference. Everything else is handled completely the same. So I think I don't want to keep you all from lunch, but if anyone has other questions, I'm happy to answer them afterwards. Thank you very much for the invitation and the chance to come and teach you. And thank you for participating. You've been a really great class.
So thank you, everyone. And this concludes the lecture part of Geoffrey's course as well. So I just want to thank again Geoffrey for sparing his time, coming here all this way, preparing this nice course and delivering it. So let's all thank him again.